Hello, welcome to Bedroom Builds at the From Python to Rust series, episode 41, Pattern Matching Revisited. Coming from the previous episode where we spoke about how we can write Python in a rusty way. In this episode, we will look again at pattern matching because now that Python 3.10 is finally officially released, that's easier available to everyone out there. So pattern matching in general is available since Python 3.10, which has been released at the beginning of October in 2021. And the Rust edition 2021 has been released at the end of October. So those big milestones for the programming languages happened more or less at the same time. In order to look at pattern matching for a comparison between the two languages, I chose to follow the PEP 636, the structural pattern matching tutorial of Python. And we'll see if we can match the features that Python offers in Rust and vice versa. All right, let's hop over to the code. So you can see up here that I'm making sure we are running Python 3.10 because otherwise the match syntax will not work. The tutorial doesn't have a full-on code, but it gives small code blocks that give you an idea of what to do. So I haven't implemented a full-on text-based game. This is just a minimal way of showing the pattern matching and not how you should write a text-based game. So in order to exit our game, there's this minimal function that quits the game. Then we have a room that we are going to use in our game and a character that moves around between the rooms. And when we go further down, we can see all of the main code that is being executed. So what's happening in our main code, we are creating a room, we are creating a character, and then we have an infinite loop that asks for our actions that we want to do within the room. Once we've answered the question, we split on the white space every word that we've typed, and then we can match onto the resulting list of words that comes out of there. So if we want to quit the application, our word will be a single item list that contains the string quit. And once this has been matched, we will print goodbye and call the quit game function that I showed at the very beginning. The same is then true for a simple command like look. This will now take the current room that we have created and have it described. And this shows the pattern matching fairly well. Here we use single items, that is easy, but now we get to more complicated one. Now we have 2 items already in the list. So if it matches look and only look, we will run this code. But if it matches look and into my backpack, then we will use the character's backpack contents to be shown. Another command we will offer is the command take. So we will take an object and then it will, and in order to take the object, we have to know where it is. So we hand off the room that the object is in and which object we are picking up. And the character will then hold this object in his backpack. Then we can drop objects. Here we see yet another pattern matching. So up here we have now the command take and any value that is a second item in this list. And now with the drop command, we actually allow to drop multiple items. So we can drop and then the star denotes a list or of objects. So any amount of list items that are shown in a drop will now be dropped. The implementation of ours is easy. We just loop over the objects and have the character drop them into the room that he's in. Next we have the go command, so we can go into a certain direction. This pattern is the same as we have seen already for the take object, for example. So we have our keyword go that is fixed in this pattern, but the direction can be any variable. And then we can change the room if there is a neighboring room in this direction by doing this code line. Then there's another variant of that, so we can now filter certain words that match a direction by using the vertical bar to OR those values. If we type either north or south or east or west, then this counts as the variable called direction that we can then later use again in the code line. That would be actually matching any word that we have given as direction up here. And another thing that pattern matching allows is adding a conditional. So here it's a silly way of doing it because this chant within a team and Wildcats match can actually be done exactly this way too. But this is to illustrate that you can attach a condition that can, for example, check an external dynamic function or something else on top of the pattern go and the chant that is matched here. So if this case now happens, then we can print out the chant of go team or Wildcats. And then we have the last case with the underscore. That is the default branch. If none of all of these patterns that we have just discussed match, then this one is executed. And here we then let the user know that we don't know what this command is supposed to mean. Good, now that we have looked at the main code of our game, let's quickly look at the implementation of how the character and the room actually work. So if we jump up to the room, we can see that it has objects that can be in the room. So if there are no objects given in the constructor, we are now creating a default list. So the default room holds a banana, a chair, and a piano. Then the description of the room will be, well, it's dark and small, and it contains the list of objects. The neighboring room can be accessed by handing the direction where you want to go. So if you go left, then you can change the room to left, and this will return a new room that contains a knife, bread, and butter. If you go north, you will have polar bear, ice, and snow in your room. And there are no rooms in those other directions. And if we don't pattern match the direction, then we have an unknown direction, and we will let the user know. And we return the existing room because we haven't changed the room. Now let's continue to the character. If we let's look at the character. Well, the character has a backpack, as we said. We are using a set. This way you can only have each item once in your backpack. And when you take an object, then we have to first verify if that object actually exists in the room referenced. If yes, we will add it to the backpack and remove it from the room. And if this object was not found, we let the user know that it wasn't found. Then dropping, same thing, only one object, one room. This way, this time we check the other way around. If the object is in our backpack, then we will remove it from the backpack and add it to the room. And otherwise, we will tell the user that it's not in our backpack. All right, let's quickly play the game. So for playing the game, I will scroll down in the code again to show the whole main function. And then let's hop over and run the game. It asks me what I'm doing next. Well, the best is maybe to look around. And here we can see we have the chair, banana, and the piano in our room. Then we can look at our backpack, and we will see that we have an empty backpack, and we see that the pattern matching works out. We have this separate command, the look backpack, that is executed. So now we can take something. So we can take the piano, and now we can again look at our backpack, and now we are carrying a piano, and it's no longer in the room. So that works. That's great. Let's change direction. So I don't know. let's go north. Let's go north, and we have changed the room to the north. Now here is of course other stuff, so we have the polar bear, ice, and the snow. Let's take ice, and we go left. So now we are in the left room, and here we can look, and this has the now knife, bread, and the butter. So since we have now ice and piano in our backpack, we can drop those. So we can drop ice and piano. And if we look in the room, now there is a piano and some ice in this room. One more pattern matching that we have is the directions. So normally, as if you remember the code, if we go west, for example, it will tell you it's an unknown direction. Since there is no difference between our pattern matching of the go direction or go to a certain named direction, this actually works out. It's the same code. But if we now try to go team, then we also get unknown direction, but we are supposed to chant the go team chant as if we were a cheerleader. So what's the problem here? Well, we can see that those patterns are matched in order of appearance. So if the case drop matches, then we will never go and even check this one. And that's our problem. So with our go direction, this one always matches because we always only have go and a second variable. This one actually never is matched, and this one isn't therefore either. In order to make this work, we have to move those commands further up. Let's do that. So we quit the game, we restart it, and now we can go team, and it works. And if we now go north, we also change the room because now we can see the ice, snow, and I'm on top of the polar bear. Great, so our game works, the pattern matching works, and it explains the first initial features of what you can do with pattern matching. That makes it much easier than to write if-else branches. And for very complicated situations, you have a very powerful tool in your hand now to match against commands typed by a user, but of course also events coming up in a queue. Let's see how this can be done in Rust. Therefore, we will exit the shell and look at the Rust code in comparison to the Python one. So quit this program, go back to the Rust code, and we'll scroll down immediately to the main code, and we'll see what the differences are. You can see that's not too bad, actually. So main starts here, and we have our current room. And as usual, we use the let keyword to define this as a new variable. And since we want to mutate the current room, we have to also declare it mutable. Then we have to call the constructor for a new room struct. So here we have a room that has a constructor called new, and this one takes an iterator. So here we are doing it in a simple way where we create a vector from those three strings, and we make that into an iterator, and from there we have our room. The character constructor, same thing, and then we will declare a valid chance vector to make the pattern matching easier readable further down. Here we then start to read from the standard input, which would match the input command coming here in Python. I'm declaring this outside the loop because we only have to access a standard in once. So here we start the infinite loop. So that's matching with the while true in Python. Here we ask the question. And since we are only using print and not print line macro, we have to make the standard out flush its output. Otherwise, we will not immediately see this message. Then we create a string buffer that will be used for the standard in reading. And here we then lock the standard in XS and read a line up until we press the enter button. And this gets fed into the mutable reference of our string buffer. We expect that to work out, so that's why I'm unwrapping that. Because if this doesn't work, then there are probably very serious issues with your computer anyways. After the successful read line, we can now split those commands into a vector of string slices. And then we can print those elements for debugging. And finally, we actually start to match as we do on the left in Python. So let's scroll down to see the full match statement. What we're doing here is we're matching against a slice that contains all elements of the vector elems. This is the denotation of this ampersand, making it a slice, and the two dots are the notation for accessing all elements. If you were to put a number here, for example, we would start at a certain index to create our slice. Now matching against this slice is then fairly straightforward. We don't even have to convert to string or something. The word case does not exist in Rust. All we have to do is use the curly braces to start and end the pattern matching. And then we can use every pattern that we want to match against. In our case, it's this slice of a vector with only one string slice in it, so quit in our case, and that looks very similar to what we write in Python. The syntax difference is in Python this works as a normal conditional statement would work, for example, so we use this new keyword case and the colon, and in Rust we have this fat arrow, it's called, so an equal sign and a greater than. That then points to what's going to happen. So here with the quit example, we have the print line first, and then we break the loop, which would be two commands, and that's why we wrap them into curly braces. However, for example, in the look pattern matching, you can see after the fat arrow, we directly call the current room's describe method, and we use a comma at the end to denote that now the pattern matching has finished, and we can go on to the next one. And here you can see the same. The look backpack is only a one-liner, and again we use the comma to continue to the next pattern match. And this is also exactly working like in Python. We can match against the first item being take and the second item being a named variable that we can use later on. So after this fat arrow, we can now go and call our character instance take method. Here we have now a string slice. Since this method takes a string, we have to convert it to a string, and we have to pass a mutable reference to the current room in order to modify the items that we take out of the room. Now the syntax becomes a bit more complicated than it is in Python. So here we have just star objects to denote we can drop any amount of objects. Here in Rust, we have also the drop command, and then we have objects. With the add character, you can make an alias the variable, and what we are aliasing here is all the remaining items of the slice. The two dots, remember up here, the two dots denote every item within the vector. So here, this is the same notation. Two dots means every remaining item in this slice. They are now aliased to this objects variable, and that's why we can actually do the same as we do in Python. We go for every object in this objects slice. We can now call character drop, and again, since these are string slices, we have to convert them to a string. The rest is fairly straightforward. We coded the same bug into the Rust code as we did in the Python code, so we have first go direction that then is always matched, and we will never actually go chant or go direction with those specific directions. To show the syntactical difference, this at sign can now be interpreted as the as we have in Python here, because here you have this or list of string slices that are valid, and then they are aliased to this direction name. Then it can be used exactly as if it was directly used like that. And then we can see the simple match with the go chant. And here we can then also see that we can do uppercase a word, and we can do a contains match against the list of chants that we have defined at the beginning. Same thing as in Python, the underscore pattern is the default one. If none of those pattern matched, we can print line that we don't understand the command. Let's compare the code of the structs to the code that we have written in Python for the objects. So first we will have the room. This is now more boilerplate, so the main code is fairly similar to what can be written in Python. But in Rust, with all the static type declarations, this becomes more syntax sugar. So first we will implement the room, which is a struct in Rust. We use the derive attribute to have our debug implementation auto-implemented for us. And the room holds objects. We have to declare that in Rust. And in order to hold objects, we are using a hash set that is coming from the standard collections. That is similar to the Python set that we have used in Python as well. This makes sure that the objects in the room can only exist each once, and every object is a simple string. Now that we have our room struct, we can implement the constructor. So in our implementation block for our room struct, we create the new method. This constructor is now a lot of syntax sugar for Rust, because we are building it in a way where we are handing over an iterator to our new method. And in order to be able to hand over string slices, we have to use lifetime. And with this lifetime annotation, we tell the compiler all of this is fine if the items that are coming from the iterator are living at least as long as this method call. And why does this work? Well, we can see that we are handing over an iterable, so something that is an iterator. This is done by this implements the iterator trait, and the items returned by the iterator are string slices. This constructor returns a self. Self with a capital S just means room. So if we ever were to rename room to another word, we don't have to recode everything, because here this stays self all the time. So here we construct self, the room, with the objects of the iterable passed in. An iterator can be mapped. And this is now why it's fine for those string slices to potentially go away after calling a new, because we make the string slice owned, meaning this is converted to a string in this case, and that's then collected into this hash set of strings. So that's the complicated constructor, but it is now super flexible. We just have to hand an iterable. Then the describe function is straightforward. We simply pass a reference to self, and then the print line with the debug annotation just prints out the hash set. Going to the neighbor, we will scroll down a bit to see the full pattern matching. So here we go to the neighbor. Same thing, string slice is the direction. Then we match the string slice, so if it's left, north, or one of those, then we print the same information that we had on the left. And here we see why the constructor is useful. We can now very easily construct a new room with certain items in them. One option is to use the vector macro to create an actual vector and call the into iterator. Another thing is you can create a mutable slice with the string slices inside, and then also call the into iterator of that. The into iterator makes this mutable necessary, because this is consuming the slice, and therefore it has to be a mutable slice. This was just done to illustrate the flexibility of this argument to the constructor. We can use a vector into iterator or any iterator that returns a string slice. Again, the use of the underscore for matching against a pattern that hasn't been matched yet. Let's continue further down to our character. This means scrolling on both sides. Again, the backpack is a hash set as it is in Python. Here we have a constructor, this time much easier. We create an empty hash set because you start with an empty backpack. Then the take method is taking this explicitly mutable reference to self because it needs to modify the character. Then we hand over the object. So in our case, that's just a string that we want to take and the room that we want to take it from. And again, this has to be a mutable reference to the room because what we are doing now is going into the room objects and check if they contain this string. And if yes, then we are now removing it from the hash set. And therefore we need to have this mutable reference, otherwise this would not work. And then we insert it into our backpack, again, the reason for the mutable self. The rest is fairly straightforward. The else and if thing matches, same amount of lines. We only add one because of the curly braces. Drop, same thing, just the inverse. We check first in the backpack and then we invert the order of commands as well. That's the Rust code. The Rust code also works. All we have to do, call cargo run. And once cargo run is run, we see a big advantage of the Rust compiler because it immediately tells us in a warning that we have unreachable patterns. And this is the bug that we had in the Python code that only got noticed while playing and the game. Here we have the compiler telling us, well, look, this go chant will never match and this go direction for certain directions will never match because there is a pattern before that that actually makes them unreachable. Anyways, this works and is broken. So if we now go team, we will just see this is an unknown direction. We can look around and we can take the piano. Then we can look at our backpack and we can go north and we can look around. You can see that the code works fine as well, but the big advantage is the compiler will tell you when you have a potential problem in your patterns. Let's jump back into the code because there is more pattern matching that is possible. Let's open this up. So we have in Python the match object and in Rust I prepared an example code that also matches against objects. For Python in the tutorial there are data classes mentioned, and with this data class decorator that we use here we can make sure that the properties of the click object are in a certain order. So position is before button. And that is important for pattern matching because it makes it easier for you to write the pattern matches because you only use directly the values that you want to match against and you don't have to name the actual attributes with that. Another thing that we will be using is an enumeration. So we have a button that can be pressed on the left and on the right side. And for this, we derive from the enum base class. Then in our main code, we create a list of events that should be matched against. So the first event that we want to match against is one variant of the enum that we've defined. So the button left in this case. Then we have a click onto a certain coordinate with the left button, and then we have a click with the right button. Then there is an object coming in, or a dict in Python, and another object, and yet again. And then we have even more clicks to show certain pattern matching features. If we scroll down in the code, we can see what this pattern matching power is doing for us now. So we're back in the main code, and now we go over every event in our events list. And each event can be matched against. So if we run into a button on the left, we can re-alias it to just the short variable, to a short variable called b, and then we print it out. Then the next pattern matching we can do, since we used the data class, is we match against the click and the coordinates x and y that are this tuple of the position. That is our first attribute. And then we can match the button that we can actually explicitly name to be the right button. This shows us that we can deconstruct the elements that are matched against. Here we can directly match the x and the y of the tuple position, and then we can use this x and y for our print command. This tree construction is very powerful and pretty cool, because right here you can actually see that we use this again, but now we use the click. We only match against the position, and only the positions where the x axis is 0, and the y value can be anything. And then we can show that we have clicked onto the x-axis by matching this pattern, and we can see then where on the x-axis we clicked. Then again, a match against any x and any y, and again we don't care about which button was pressed. We can again use this deconstruction to show the x and y, and here we can now use the powerful matching against those objects coming in. So this object, or this dict, has a key called text that is a certain message. So now I can access the message that is coming in with the variable message, and then I can match against the color, and here I can actually match against a primitive Python type, in this case a string. So the color has to be a string in order for this pattern to match. So if the color was not a string, this pattern would not match. So now after this deconstruction, we can print out showing then the message variable and in the color C. And yet again, another pattern matching against those objects coming in. Here we're matching against the sleep key, and it has to be a float. And this float is then used as time. And then we can print that we are sleeping this amount of times seconds. So going through those pattern matches in Python, we can understand that when we match for this sleep float, that this sleep long will actually never match to any of those event matches and therefore will be ignored. So how can we pull this off in Rust? Because that's fairly powerful dynamic programming right there. No, we create a list of very different things. So here we have an enum. Here we have a click instance. Here we have a dict instance. And that's all mixed in one list, or one vector if you want in Rust notation. So Rust can do that, but not directly like that, because we have to have a well-defined vector with that holds elements of a certain data type. We cannot mix the data types. One option that Rust allows us to do this anyways is using the enum dispatching. So in order to match the code, what we did is we created the enum button with left and right. And in order to be able to print them out, we also derive the debug. So that matches our left and right button enum for Python. Then we create our struct click. We don't have to use a data class because in Rust, the order is kept by default. So here we have our tuple with the two values, and our button is of the enum type button. Then we have our text color that holds the text and the color string. So in Rust, we cannot match against a random dict or hash map. In Rust's case, we will have to create actual objects. So in our case, we have this text color one. and therefore the matching will only work against two of the type string. If there was a text color coming in with the color being the integer value of the color, for example, this will not work. You would have to create a specialized struct that represents a color being an integer. Now we get to the powerful part. We can create an enum that holds different items. And that's what we are doing here. So we have an enum called event, and the variance that we allow is actually a button. So what we are doing here, we have the variant called the button that holds a button. That's a bit confusing, but that's mostly how Rust programmers will do it. So we are holding this enum button inside a variant of the event enum called the button. Then we do the same for a click. So the click will hold the click. Text color holds the text color. And what we can also do is directly actually come up with our own small types. So here we now create a sleep text that holds a sleep string, and we create a variant called the sleep that with the same attribute holds an F64 afloat. And the cool part now is we can use those event variants to be elements inside a vector. So we can create a vector of events, and then we can use any variant inside this vector. That's exactly what we are doing in the main code. So let's hop to the main code. So the creation in Python of this list is exactly what's happening in this block here on the Rust side. What we are doing is we are only using the event variants. So here we use event button to hold the variant left of the enum button. So that is this first line. Then we create a click with a certain position and a button. And this matches those lines on the left, becomes a bit longer. Then in order to create a text color, we have to make two strings and not string slices, because the text color holds actual strings. Same is true for our sleep text. This sleep long becomes the enum variant sleep text of our event, and this one holds the attribute sleep, which is a string. And then we can also create our sleep in variant with the float, and then again the two clicks as above to match the code in Python. Once we have that vector, it's a valid vector because this vector is of type enum event, and it allows all those variations. With this enum dispatch, you can write a very powerful and very fast code, because the compiler knows which variants exist, knows the size of them and everything, so you can write very optimized code. There are even crates out there that can automatically write those enum dispatching variants for you to, for example, implement a very performant network protocol where you have a certain list of commands that can come in. That's a perfect enum application. Right, let's continue down with our Rust code. So now we enter the loop that we also have on the left in Python. So we match every event that is found in events. Same thing for event in events, we match the event. And in our case, we now have to match against the enum variants that we have defined. So this event is an enum of type event, and the variant button holds a button. We have aliased it to the name b, and then we have the same code as we have in Python, except that we have to use the debug output formatting. Now we can also match against the XY and destructure the XY out of this. So here we have the click position, and we get to then use that in the print line as we do in Python. And we can match against the button that was pressed on the right. And then we do the same thing we do here with matching against the X on 0. And in order to ignore the button, Rust doesn't allow us to not mention the button. We will have to use the underscore. This means we don't care about what button is pressed. Same thing down here, destructuring again to X and Y, ignoring the button. And for our text color, we can directly match against this text color thing. Again, we have access to the message and color. Color we don't have to write twice, because if we want to call it color, then we can simply use the name that's found here and can use it directly in the print line. And finally, we match against the sleep with the float. And here we can see that we can use that with the t seconds. So, and at the very end, we have the underscore matching against every pattern that hasn't matched so far. And here we just continue with the loop. This is very explicit, but it also helps other programmers to read your code, because here they see very explicitly what's going on. One big advantage that I will show you by running the Rust example is the compiler complaining that field is never read sleep, and that is true, because it is a sleep text with the string variant is never matched in our pattern matching, and therefore we never access this variance argument, and therefore this is a dead code to the compiler. So this warning already gives away that you have forgotten to match against this variant. And that will bring me to another point that I will show you later. Now let's look at the output. So the first event that came in is a button that is of the variant left. Then we clicked on 2 and 4. Then we have a right click. And here we can see that we have showed text blah in the color blue. And we are sleeping for 1.3 seconds. So all of these pattern matches work out. And we can also see that when we click on 0 and 4, that we clicked on the x-axis. What we can also see is that the event with the sleep text has been ignored, so it never matches any pattern. So we just jump into the continue, and it doesn't show up anywhere here. And we can also see that you have to be careful with your pattern matching, because here we have 2 times the click instance with 0 and 4. One time we click the right button, one time we click the left button. However, we can see that up here we have a pattern that matches against any X and any Y for the right button press. And this shows us that we have a right click on 0,4, even though we likely wanted to have the x-axis being printed out. So there are certain things that the compiler cannot save you from if you match against all the variants possible, but you write the bug like this into your code. This is still being executed in order of definition. So this one matches first, therefore the x-axis special variant is not executed, and this might not be what you want. However, I started already explaining that the compiler tells you that you have screwed up potentially because nobody's ever accessing this variable. Now, this is also what Rust does for us. So if we now change the code to not have the default matching, we will see that the compiler does not like us anymore, because it will tell us that we have never matched against this sleep text pattern, and therefore this whole matching of the event is incomplete. That's another reason why this enum dispatch is very powerful. If you use that, you can make sure that every event variant, in this case, is handled by your code. So if somebody extends this enum definition and adds another variant, and you have matches in multiple locations against the events coming in, you will actually have to implement those events there. Otherwise, the compiler will not be happy. So there are 2 solutions to that. We either uncomment the default handling and the continue, or we implement an actual match against the sleep text variant, and then the compiler will be happy. Let's do the latter, and we can actually directly use the pattern that he tells us, because we don't really care about the string version. We have no real use for that. So we'll use this sleep text with the 2 points to show that we don't care about the actual contents of this variant. Let's quickly add that code and see if this makes the compiler happy. So we have added exactly what the compiler proposed. So we want to match against this sleep text with the 2 columns. And we continue because we don't care. However, we keep the default match for any pattern that hasn't matched commented. And let's see if the compiler likes that. So we write it out. We hop over and we run the example again. We still get the warning that nobody ever reads this sleep attribute, which is very good because it shows us that this sleep text variant is not really used anywhere. But the code works and executes fine. And now we can use the advantage of the Rust compiler to make sure that we always have exhaustive pattern matching. Thanks for watching. Coming up next on the From Python to Rust series will be the builder pattern, or a workaround for having default values for function arguments in Rust.